Hello everyone, my name is Vahid. I'm a PhD candidate at University of Quebec in Montreal. Today I'm going to present our project titled as Empowering Dairy Farmers with a decision-making framework using a transformer-based model. During the past 5 decades, the world population increased dramatically, and because of this increase, the need for food production raised, and in order to address this demand, the dairy agriculture was the most important sector in order to address this population raise. Dairy farming is the most part of the dairy agriculture sector, which has been under innovation through data-driven methods. For example, people use the AI, artificial intelligence and the Internet of Things to provide tools for the dairy farmers, and in order to help them optimize their products, especially in the dairy industry. Milk production is really important because it's the most important part of the people's diets worldwide. As I mentioned, bringing to the farmers precision tools is important in order to help them manage their milk production and increase the health level of their animals. Unlike humans, decision making is really time consuming decision making is really time consuming for the humans, but AI driven methods are really fast and efficient, and they can provide very useful suggestions to the dairy farmers. Here in our project, we use the information to the dairy farm over the first and second lactation, and provide these the collected features over the early lactation to the model, to the prediction model, to provide the cumulative milk income in the upcoming lactation to the dairy farmers. And the decision-making framework uses this provided predictions to provide recommendations to the dairy farmers. Prediction of the cumulative milk income can be stated as a multivariate time series prediction model, multivariate time series problem. And here, since the dairy factors include different variations like health indicators, milk quality, management, seasonality, and milk income, so we had to use all of these variables over the early lactation and treat them as multiple time series, and pass all of the dairy series at the same time to the prediction model, and get the predicted cumulative milk income in the next lactation as the output of our model. As you can see in the figure, the time series, as I mentioned, dairy time series is multi-channel because it includes multiple dairy factors recorded over the early lactation. And the output of our model is single channel, or it contains only one time series corresponding to the cumulative milk income. And the decision-making process is done by comparing the predictions and the ground truth cumulative milk values. I want to have a brief introduction to the related work and literature review in time series domain. Time series prediction models are divided into two main categories, statistical models and deep learning-based models. Here in this project, we focused on deep learning-based models like transformer-based models, linear models, recurrent neural network models, and convolutional neural network-based models. Our motivation to propose our framework was to capture the temporal correlations and also to represent the dependencies between different time series or inter-series dependencies. So in order, first of all, we plotted autocorrelation of the milk values or milk income over the first, second, and last lactation in order to indicate the dependencies between different time steps and illustrate the importance of specific time steps or specific months over the lactation periods. And also on the right-hand side, you can see the dynamic time warping distance between their features by considering their temporal dimension. As you can see, the dynamic time warping distance between specific variables are very close, indicating that they are highly correlated and dependent on each other. So this kind of dependencies should be captured and modeled by the forecasting model. We also visualize the different daily time series over the first and second lactation to indicate similarity in their seasonality and trend. For example, on the left, you can see the time series of milk yield and protein over first and second lactation, and the similarity between their trend and seasonality. By considering these kind of correlations, I mean the temporal and spatial or inter-series correlations, we decided to modify the well-known transformer model in order to capture the temporal dependencies over the lactation months and at the same time model the inter-series correlations. Multi-head attention is the main component of the transformer-based model, which represents the temporal dependencies between each pair of time steps. And since we use multi-head, it captures those dependencies from the different perspectives or in different dimensions. Here in the middle bottom figure, our main model is illustrated. It contains four main components, temporal and spatial encoders. Temporal encoders, represent the dependencies on temporal dimension, and the spatial encoders captures the cross-channel dependencies and utilize all of those dependencies in the prediction result. And the final forecasting result is the weighted aggregation of all predictions. In order to assess our proposed model, we used a real-world daily data set, which includes 100,000 training samples and 47K test samples. We set the input lengths of our model as 22 because the mean, because we calculated the average lengths of first and second lactation, and the lactation lengths for each lactation number was almost 11. So we set each lactation period as 11 months. And since we feed two lactation periods as input to our model, we set the input window as 22 and the output window as 11 months or 11 steps. Here you can see the different hyperparameters which were used in training during training our model. We evaluated our model using different error metrics which are commonly used in time series domain. For example, mean absolute error, rooted mean square error are calculated based on the difference between the predicted cumulative milk income and ground truth ones over the target lactation months. We also calculated the cumulated mean absolute error and the cumulative root mean square error, again based on the sum of the predicted cumulative milk values and the ground truth ones. Here in this table, we reported the error measures related to our transformer bits model and other state-of-the-art models. As you can see, in terms of error metrics, our model gained the lowest possible error, especially compared with ARIMA, which is a classical and linear model, and also compared to NBITS model, which is a univariate model. Our proposed framework gained the lowest error. We also devised a simple procedure to provide recommendations to the farmers by using the output of our model, which are the predictions over the third lactation. Our procedure firstly calculates the mean and standard deviation of the cumulative milk values in the last months of the third lactation, and by comparing the mean and the standard deviation of the predicted cumulative milk income by the ground truth by the calculated ground truth mean and standard deviation, we compared the kept and dropped animals, and finally we calculated the accuracy or percentage of well predicted animals by comparing the ground truth and estimated incomes from our model. We used three different perspectives to calculate the threshold for keeping or removing animals. The first one is the normal threshold, which is the mean average of the cumulative milk income over the test animals. And if one test animal's cumulative milk value was higher than this threshold, the animal should have been kept. Otherwise, it was removed from the herd. The other two perspectives are a little restrict, and the other one is the first one, the consumerist one, is less strict, but the conservative threshold is more restrictive by adding half of the standard deviation of cumulative milk income to the average cumulative milk value. So we provided we calculated the decision accuracy by taking into account the percentage of well estimated or well predicted animals. Again, compared to other state-of-the-art models, our transformer bits model gained the highest amount of accuracy from three different perspectives. And also, our model obtained the lowest overestimation error. By overestimation error, I mean the percentage of the animals which should have been removed while the models kept them. From the other perspective, conservative perspective, again, our model obtained the highest accuracy of 78.66%, higher than other models. And finally, from the third perspective, consumerist perspective, our model obtained accuracy of 79.80%. And this highlights the efficiency of the model in capturing the dependencies over different lactations, and also, and at the same time, capturing the dependencies between different dairy variables. In conclusion, we proposed a transformer-based model to predict the cumulative milk income in the target lactation by using the multiple dairy variables recorded over first and second lactation. By analyzing the dairy dataset, we concluded that the dairy dataset follows a specific trend and seasonality based on the length of the lactation and different seasonality effects. Also, we concluded that our forecasting model captures different aspects of the dataset, including temporal and spatial correlations. And the predictions provided by our model were used in the decision-making process. And in future, we are planning to generalize our model to different scenarios, including different lactation numbers, and at the same time providing decision-making after different lactation numbers to the dairy farmers. Thank you for your attention.
Thank you very much for that. Any questions? If you have, please feel free to come up to the microphone. Do you want to ask a question? Okay, please. Yeah.
Thank you. Nice presentation. My question is, you trained a model on 2 second lactation, right? 2 lactation. Did you try your model on only 1 lactation period to give the farmer more insight? Or do you need that full 2 years of data to be able to predict the 3rd year?
Yeah, it's a good question. I didn't try giving only 1 lactation to the model, but the model is flexible to receive the records of 1 lactation, but it should be trained from scratch in order to generate the predictions of the second lactation given the records of the first lactation. But it's doable to predict. Yeah.
And maybe a follow-up question if we have time. Okay, good. Yes. My follow-up question: did you try to maybe mask some part of the training set? So let's say that you are unable for a producer to get some data one day because it's impossible for today to get the data. Did you try your model with I would say noisy data, which you mask some of the data to see the performance of your model?
Actually, no, I didn't mask the inputs, but our dataset had a lot of missing values, especially in some health indicators. There were a lot of missing values. So I imputed the missing values before training the model by average of herd or seasonality. For example, I grouped the animals based on their herd number and test year and test season, and after that I calculated the average inside each group and replaced the missing values inside each group using that average. But I didn't mask the part of the input.
Okay, well.